Good afternoon, Fancy Meat Computers. How is everybody today? I hope you're feeling better than I am. I've got a cold. It's the worst. I'm just checking to see what the dealio is. Where we left off last time. See here. That looks about right. No, that might not be still it though. Okay, so we did take, we did this one. Okay, this is where we are. Good. It's kind of cool how you can watch the video back, eh? Yeah. Well, there are only 6 people watching at the moment, so... Nobody here but us chickens. Let me check to see if we have any announcements today. Actually, I'm feeling better at the moment than I was this morning, which means I might be able to get some productive work in today, maybe. Aside from teaching this class, which is always productive. Yep, that looks like it. Oh, Can I talk about assignment 6, question 3? Yeah, actually, I had a Piazza question, which was, I did a, I think a pretty good hint. So I'll just give you the hint I gave on Piazza. But I can talk about this in more depth if you want. So, if we take a look at the way in which we're proving, what is it that we're proving in that? Let me look up the, let me look the bloody thing up. Let's see, preservation, yes. So, we describe a proof of the preservation property of typed arithmetic expressions. This proof is inductive over typing derivations. We organize the proof so that it is inductive over evaluation derivations instead. So, to read this, so it's not too bad really. With the version in the slides, you do a case analysis first over the typing rules, and then use evaluation rules applicable to whichever rule you started with. The question asks you to reverse that fact. Start off with a case analysis over all the evaluation rules of UAE, or TAE as it is, and then analyze them in light of the typing rule applicable to the term and information that this yields. So, in other words, in the case of TAE, there we go. Essentially, you see how we're doing a case analysis over all of the typing rules? We've got 7 of them in total. Typing rule semantics somewhere. Well, that's part of it. Yeah, so that's part of it, and then the rest of it is elsewhere. So, in the slides, we start here with the typing rules, and then we apply applicable evaluation rules based on the terms that you derive from the typing rules, right? So if you used tpred, then the thing you're using tpred on will be of the form pred t1, which in theory means that you should know that the only evaluation rules that could possibly apply to it are epred, epred0, and epred successor. So those are the sub-cases that you have to go by after you've established the typing rule. So the thing that's being asked for in the question is to produce the inverse of that. You start off with the evaluation rule, and then you select whichever or how many ever of the typing rules are applicable if the original term was of the form required by the evaluation rule. Fortunately, whereas one typing rule leads you to multiple evaluation rules, each evaluation rule will lead you to only one typing rule, because we have a one-to-one correspondence between typing rules and terms. We only have one typing rule per term, whereas with evaluation rules, we had as many as 3 evaluation rules that would apply to any particular term. So that's what the question is asking. Hopefully that's reasonably explicable. Hopefully that's a good yep. There we go. I think it was mine, but I haven't looked at it. The word reverse would have been nice in the question. I thought using the inversion lemmas was just the limits of all to... yeah, well, I mean, you know. Yeah, so the thing about the question is that it doesn't give away, it doesn't give away the structure of the, pardon me. It doesn't give away the structure of the proof of the preservation property. You're meant to understand the structure of the proof of preservation prior to attempting the question. Or ask someone so that you may understand it better. But yeah, no, it's, you know, it is what it is. For induction over evaluation rules, is the base case any rule that could just yield a value? Yeah, you may have noticed that as we've been going through the course, we are speaking less and less about the base cases. The textbook basically takes the position quite early on. That is, the textbook takes the position quite early on that the base cases are hardly ever interesting and hardly ever worth mentioning. I would take the position that that might be true in a graduate class where, people are of a more advanced mathematical persuasion, shall we say. But in the course of an undergraduate class, it is useful and interesting to still state the base cases explicitly. Yeah. I'm not having a fun time. I don't think it's the mad virus though. I think it is a bacterial infection because when you get to my age and you've had enough colds, and you're sufficiently attuned to your body through either meditative practices or some sort of, martial arts training, because that also attunes you to your body, you can tell the difference between when you have a virus and when you have a bacterium. And I think at this point I have a bacterial infection rather than a viral infection. But yeah, I'm not my usual peppy self, eh? But anyway, back to induction. So when we do induction over, typing over typing derivations is pretty, it's pretty, typing derivations. Yeah, it's almost precisely similar to the evaluation derivations. So if you know how an evaluation derivation works, you know how a typing derivation works, and if you know how induction over evaluation relations works, then you also know how induction over typing derivations works. But yeah, that's essentially it. Yes, is you the base case of any derivation chain is something to which no further derivation need be applied. In the case of our derivation rules here, what that essentially means is any of these rules that doesn't have a line in it, right? If you have no premises, then you have nothing, like you require no subderivation. So your base cases of a derivation induction would be, in this case, of course, true and false, and of course 0 and successor of a numeric value. Those would be your base cases. Now they're not like, you may have noticed in the slides that I'm not as often saying like this is the base case, it's kind of just like we get the evaluation, we get the cases for the values typically out of the way first, because they're usually very easy. So yeah, what about fungal infections? I don't think I've ever had a fungal infection, but I could be wrong. No mushrooms sprouting out of my head, so that's a good thing, usually. Certainly a good thing in the video game for the SNES Earthbound. All my Earthbound bros in the crowd will know what I'm talking about. So yeah, hopefully that's a sufficient description for that. Are there any further questions about any of that? Because if not, we should see if we can wrap up this, not this one. This one. We should see if we can wrap this up today. Except not being turned, Nick Toad, yeah. Yes. Oof. Oof. Yeah. Well, If I'm a fun guy before, how much more of a fun guy would I be after? Duh-dum. So we have a section at the end here to talk about the properties of the typing relation over lambda calculus in a very symmetrical way to the typing relation that we had over untyped arithmetic or typed arithmetic expressions. So essentially, once again, we are interested in proving both the progress and the preservation of our typing system. Both of these properties are necessary in order to verify the soundness of the type system, which is, of course, the whole point of having a type system in the first place. So, let's prove progress. Just to remind everybody, the property of progress, as it applied to typed arithmetic expressions, was that if you have some term which is well typed, it can't be of wrong value, essentially. It's either a value or it can be evaluated, right? So it can't be a normal form that's not a value, essentially. This is like the base case for our inductive, the inductive structure of these two theorems. The base case demonstrates that you're not currently stuck, and the preservation indicates that the property holds after after any particular typing or evaluation step, which means that no matter how far you evaluate it, you never get into a case where you lose the property of it being well typed. And since we know that every term that's well typed can also be executed unless it's a value, we can therefore conclude that the whole thing works without getting stuck. So, brief parenthetical note. You remember this business that we were talking about with if statements and how it's like normally the way that we deal with if statements is to constrain the we constrain it so that T2 and T3 have the same type because otherwise it's untypable. Remember that? I think I've got that in here somewhere. Yeah. Yeah, here. So the way that you can get around this, like it's impossible to get around this problem under simple type theory. But if you introduce the concept of polymorphic types, suddenly this becomes possible. So one of the things that allows us to draw our boundary between well-typed, it allows us to draw our boundary between wrong values and correct values much closer to the wrong values. One of the things that allows us to get there is polymorphism in typing, which is a thing that I'm not sure which languages will do it particularly. I haven't read the chapter on polymorphism, but I know that that's in the textbook, so that's one of the mechanisms you can use if anybody was curious about how we might go about solving this problem in a manner that maintains our guard against wrong values. Anyway, so the theorem of progress as applied to typed lambda calculus is as follows. Theorem: progress of simply typed lambda calculus. Suppose that T is a well-typed term with an empty typing context. That is, turnstile T has type T for some type T. Either the term T is a value, or else there is some term T prime such that T evaluates to T prime. so that's our preservation property. It's actually, the only difference here between this and the TAE definition is the assumption of an empty typing context. So, because we're assuming an empty typing context, we should explain why. So the reason we are assuming that the typing context is empty, is that if we can prove it for an empty typing context, then we have proved it for all typing contexts, right? This kind of leans on a property of the typing context that that is sort of implicit in our discussion of the typing context so far, which is that when you have a typing context, it allows you to type more things than when you don't. And that you cannot, it is impossible to, you can't run it in reverse. Having more entries in your typing context will not make things untypable that were before typable, right? Adding information, do we need a theorem for this? No, let's just not worry about a theorem. Let's just go with our intuitive understanding of it. It's this is actually a bit that's not explained at all in the textbook, which means he assumes that you would be able to figure this out if you just thought about it sufficiently long. But yeah, so because the gamma, having more entries in the gamma allows you to type more things, right? Removing things from the gamma allows you to type fewer things. So if you can prove this under the condition of no typing information in gamma, you can't have less than no information in gamma, right? So that means you've proved it, and you can't, because you can't have something that become untyped by adding something to gamma, that means that it's this will hold for everything in any context. So we will pursue a proof by induction over typing derivations. Let's get our case analysis hats on. So let's first address the Booleans, right? So we proved progress already for Booleans when we talked about typed arithmetic expressions. Question to the class, without reading the next bullet point, is there anything about TLC that would invalidate our proof of progress for terms of TAE? Wow, this doesn't really work as a quiz. Nope. So let's save the time, ourselves the time of repeating them. Yeah. So because the Boolean terms never really touch the lambda calculus terms in terms of the lambda calculus term evaluation rules only apply to lambda calculus terms and vice versa. So pardon me. So as a consequence of that, we can just say, go read last lecture, and you'll know if we can hold progress for them. So let's move on to our newer and slightly more interesting terms. Let's consider t-var first. So consider the premise of t-var. We have x typed t as an element of gamma. Remember that we assumed that gamma is empty, right? So since there's no elements in gamma, there can be nothing that's an element of gamma. 360 audio simulation with Nick blowing his nose. Oh, I'm sorry. One of the students in 1MD3 this morning wrote nose blowing ASMR in the in the chat, and I giggled, because that would also be equally terrible. So anyway, so gamma is empty, meaning that there cannot possibly be any x which has a type t being represented by it. So this is actually an invalid premise, right? Since nothing can be an element of the empty set, t-var can't be used under our current set of assumptions. So we don't have to worry about it, actually. It's like, this is vacuously true. Remember, if the premises are false, then you can derive either true or false as a conclusion. That's the principle of explosion, right? So in this case, we have an invalid premise, which is fine. Not all invalid premises are bad, as it turns out. So let's move right along to T abstraction. Lambda abstractions are values under typed lambda calculus. So our theorem is trivially satisfied. Easy, right? T abs, if we're assuming that T abs is applicable, then we've already got a value, right? We want to say that T is either a value or there is some term such that T evaluates to it. So really the only interesting case here is T app, that is to say, the typing derivation for application, function application. From the fact that we have applied T app, we can immediately derive the following correct information. Number one, the term that we are analyzing has the form T1 T2, right? T2 is applied to T1. We can immediately state that the type of T1 is T11 begets T12. I think I've decided to use the term begets to represent this arrow. And also that T2 has type T11. And note for these final two, we are also dealing with an empty typing context, just like, just like before. So, via the induction hypothesis, either T1 is an element of V, or there is some T1 prime such that T1 evaluates to it. This is the power of induction. Also, via the induction hypothesis, either T2... Oh, I left MathCal in. Ha! That's funny. I am sorry. Either T2 is an element of V. MathCal is the latex tag for, like, cursive or calligraphic. It's calligraphy. Or T2 evaluates to T2 prime. So basically we've now got 4 cases that we need to consider, which are handily represented by the above chart. So either T1 and T2 are both values. T1 evaluates to T2, or T2 evaluates to T1. Right? So, if T1 evaluates to T2, under call by value semantics, the one that we use is EAP1, regardless of the state of T2. Right? That's call by value semantics. If the first term in an evaluation can be evaluated, it will be. Secondly, if T2 can be evaluated, and we have not hit the case where T1 can be evaluated, we apply EAP2, which is our second congruence rule, which allows us to evaluate the second term in the application. Only in the case where both T1 and T2 are both values are we permitted to apply EAP abs That is to say, application of a term to a lambda abstraction. So, applications of EAP1 and EAP2 are immediate from the evaluation rules, but EAP-ABS requires a bit more explanation. In order for EAP-ABS to be applicable, T1 must be of the form lambda x of type 11, T11, dot T12, so it must be a lambda abstraction, and T2 must be a value. So we know that T2 is a value, because that's given. So really, we're deciding between T1 being a lambda abstraction or it being some other type of value, such as a variable or true or false or something like that. So, we can use clause 2 of the inversion lemma to deduce T1 has been in the correct form, because we have previously stated that T1 has type T11 begets T12. So just pulling our inversion lemma back up again. If or is that the inversion lemma? That might just be the typing rule. Let me think here. Blah 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 blah. Inversion lemma R. Yes. So, yeah, so the inversion lemma for this guy means that we get hold on a tick. I think I'm confusing myself. Did I actually say that I'm using the inversion lemma here? Inversion lemma. Yes. Where's my textbook? I'd hate to be telling you things that weren't true. Sorry again, folks. Just give me a moment here. It's not the inversion lemma, it's the canonical forms lemma. Right. So, thank you, textbook. There it is. So, via the canonical forms lemma, not the inversion lemma, if we have a value of type T1 begets T2, then we know it must be a lambda abstraction, which is good because that's how that works. Because we know that T1 is a value, and we know that it has type T11 begets T12, so we know that it must be a lambda abstraction, which means that we know that the EAP-ABS must be applicable to it. Progress, therefore, holds for all typing rules of TLC. Quod erat demonstrandum. Ta-da! Any questions about that? Canonical is basically get its form from its type. Yes. Yeah, that's it. That is, yeah. Yeah, that's the purpose of the canonical forms lemma. Is if you know the type, you can derive, and you know it's a value, then you can get what, like, you can get what value it has to be, right? So yeah, and whereas the inversion lemma, the inversion lemma is primarily interested in deriving the types of subterms from the types of the terms themselves. The inversion lemma is primarily used or useful for inverting the typing relation itself. That's why it's called inversion of the typing relation. Whereas canonical form, again, is you can get the value out from the type. So, good. I'm going to blow my nose, so close your ears if you don't want to hear this. I can't imagine why you would want to. So we've proved progress. Now let's see if we can prove preservation. In order to support the proof of preservation, you will need to work together. You will work together to create the proof of preservation itself in tutorial next week. First of all, next week's tutorial, you're going to do the proof of preservation, but in this lecture, we're going to cover some of the theorems that you'll need in order to do that. So we're going to have two lemmas and then a theorem, which is actually a lemma because we're using it to prove a different theorem specifically. But we're going to do a lemma of permutation. We're going to do a lemma of weakening. And then we're going to do preservation of types under substitution. This is, so preservation under typing, preservation under evaluation is like, we've already kind of done it, so we, but what we haven't described really is preservation over substitution. That's like new territory for us in lambda calculus versus UAE, so that's what we'll be focusing on. So, the first of the, okay, so we're the first lemma here, permutation, states that the elements of a typing context gamma may be permuted without changing what is derivable from it. This is, if you've been thinking about gamma as being sets in set theory, then this is trivial. This is a trivial property. If you've been thinking of gamma as being composed via some grammar, however, this is not necessarily obvious, although it is pretty darn obvious. So, if we have some gamma, which has which proves some t, and then we have some delta, which is a permutation of gamma, then delta also proves the same thing. Moreover, the latter derivation has the same depth as the former, so it doesn't change anything structurally. You all know what I mean by permutation, I hope. Do you know what I mean by permutation? Permutation has a very specific meaning in mathematics. Essentially, a permutation is a reordering. So if I have, derivations 1, 2, and 3, 2, 3, 1 would be a permutation. 3, 2, 3, or 3, 2, 1 would be a permutation. It's a very simple concept in statistics, right? So it's like anagrams, right? So if I have the word car um, what's a good anagram? Well, anyway, if you have numbers 1, 2, 3, 4, 5, permutations of this number include this one, that one, etc. Basically, it's a rearrangement without duplication or subtraction. Act, tac, cat. Yes, exactly. You rearrange the elements of the thing without making any additions or making any subtractions. Right? So it should come as no surprise then that if delta is a permutation of gamma, then it proves the same things as gamma. Primarily because the element of operator doesn't care about ordering. That's the primary thing about that. So that's fine. Now let's talk about the weakening lemma. It can also be said that if we derive t having type t from some gamma, then we can add more elements to gamma without changing this fact. We can't necessarily take away elements, right? It's not possible to take an element away from gamma and claim that it still proves t, because you would have to rederive t from gamma, right, to demonstrate that. However, we can add elements to gamma without having a negative consequence on what is provable from gamma. More formally stated, if gamma proves t has some type t, and x is not an element of the domain of gamma, then gamma concatenated with x proving type s altogether still proves t has type t. Moreover, the latter derivation has the same depth as the former. What's the difference between gamma and delta? Usage difference. There's no usage difference particularly. If you look at the Greek alphabet, it's alpha, beta, gamma, delta. So delta is just one Greek letter up from gamma. So it's like naming a... It's actually exactly the same as like pulling in type S instead of type T. It's like you just offset the name by one character in the alphabet, and it means basically the same thing. The delta here is the same thing as gamma. Structurally, it's just a relabeling. Hopefully that makes sense. So, so the proof of this is straightforward induction on typing derivations. I'm not going to do it in lecture because I'm asking you to do that on assignment 7. Come up with proofs of the two of those. As I've said, they're both pretty straightforward and they should be pretty obvious. So both of the above lemmas should be fairly obvious and boring. The properties, however, will help us prove that well-typedness is preserved when variables are substituted with terms of appropriate types. This property, so the substitution thing here, this property is so ubiquitous for safety, for the safety proofs of programming languages, that it is often referred to just as the substitution lemma. So, substitution lemma 1, preservation of types under substitution. So, we shall say that if we have some gamma concatenated with x proving to s, or x of type s, and that yields t of type t, and gamma yields s is of type s, then we can say that gamma proves that x substituted for, or s substitutes, if you substitute x for s, you still get type T in T. So it's a little complicated. But essentially, this is the description. So we have some type. We have some term that evaluates to some type T. If we already know that X has some type S, and we also can derive that S has some type S, the substitution can be performed without modifying the type of T. So this is actually somewhat stronger than preservation. Preservation over evaluation derivations does not necessarily state that you get the same type before and afterwards, right? It's just maintaining the property of well-typedness. In this case, we're saying something a little bit more strict. We're saying that T will not change its type. And from that, we can also derive, trivially, the property that it's still well-typed, right? Good. Another way to state this is that if we have some X which gamma types as S, and then we have some S that has the same type, we can substitute X for S in T without the type of T changing. Proof will proceed by induction overtyping derivations and using case analysis overtyping rules. Just as a reminder, we're going to need our substitution rules, so here they are. Question. So we can actually perform substitution that changes the term's type. Oh yeah, absolutely, but the requirement of it is that you're changing X for something that doesn't have the same type as X, right? So, for example, you could come up with a pretty trivial example of this, actually. So let's say we had some lambda. Ha! There you go, Mark. I just used compose mode. Lambda x dot x, right? Let's assume this is lambda x expecting type bool and then we applied to this, you know, some x to s, and we also know that s has type nat, for instance. If we were actually to perform this substitution, then you'd get lambda s dot s, but the type of lambda would also be changed to nat, right? Even like this, you can see how this is like also a syntactic conflict. We don't really have a substitution rule which allows us to change the type of the argument like this, but we're doing it anyway just to demonstrate how broken this example is. So, you know, this would change it from, so this would have been typed before as bool to bool, right? Well, yeah, and then it would become nat to nat, in theory, I think. Which, you know, is not what you want. You want the typing to remain steady, constant, stable. Plug the GitHub. Okay. So, Mark has come up with this very cool. You know what, Mark? I'm going to talk about it once class ends, because I've got I want to do a little bit more here. So, we can at least get through the base case. Let us first consider T true, the typing rule for true. Wow, that's interesting. I guess you can post links because you're moderator, eh? Most of the time, people can't post links. So, T true. if we have t true, then we know the form of the term t is true. And we also know that the type of t is bool. If t is either a Boolean literal, so if t is either Boolean literal, that is to say, if it's true or it's false, it's unaffected by substitution operations, right? You can't do anything with it. There's no substitution to perform. We can therefore conclude that gamma, the typing holds throughout substitution trivially because, no substitution is performed. Of course, this argument also applies to t false. So let's consider t if. And this one will be the last one for today. So the form must be if t1, then t2, else t3. And we know that t1 must be typed bool, t2 must be typed some type t, and the same for t3, given the typing context that we started off with, gamma plus x yields s. So, via the induction hypothesis, we can say that the typing holds through substitution for all of the subterms. So, from here, we can apply the typing rule t-if to conclude that the overall term must maintain its original type, which is t. Thus, well-typedness is preserved under substitution in this case. Of course, this kind of implies a substitution rule that we haven't actually explicitly stated yet, which is that if you have an if-then-else, a substitution simply applies itself through to each subterm of the substitution. I just thought of that, each subterm of the if-then-else, but that makes sense, right? In the same way that it applies itself to all the subterms without really doing anything except applying itself to the subterms for application, it would do the same thing for if-then-else. So yeah, there we go. Okay, so I'm gonna plug Mark's project now. So on Linux, I don't know how many of you folks are Linux users out there, but there's a way that you can access. Welcome to the weirdest way to define currying. Yeah, no kidding. There's a thing that you can do with your keyboard, right? Which allows you to access just a huge number of custom defined shortcuts in Linux. It's called compose mode. You can go into your keyboard settings and set one of your buttons to the compose button, which means that you can define all kinds of customized shortcuts. So one of the things, if you don't mind me showing the code here. So Mark's been working up a file with all kinds of interesting and useful things. So you can actually hit the compose mode key and then type the name of the Greek letter and get the Greek letter in Unicode, which is pretty cool. So yeah, and you can do it with a bunch of math symbols as well. But essentially, it's cool because you can define as many of these as you like. If anybody wants to contribute to the project and thinks that might be a useful thing, like I just used it in lecture to be able to type, you can type Greek letters with it with frightening ease. Which that looks like K, but it's actually kappa. There you go. Upper lowercase lambda. Lowercase delta. Uppercase delta. All kinds of stuff with very, very cool, just, straight keyboard stuff. And it's like operating system wide. Like that's one of the really, one of the really cool and neat things about it is, normally when you set up these types of shortcuts, it's like each particular program you want to do this in is gonna, like, you're gonna have to set it up for, you'd have to set it up for each individual program, but this is like an operating system wide thing, like it's attached to your Linux user. So, so yeah, it's like, doesn't matter where you are, you can just enter it. Why did Kappa get replaced with a moon emoji? I don't know. Why did Kappa get replaced with a moon emoji? Are you telling a joke? But, like, you can just, switch between applications and the same shortcuts apply, which is very cool. Read my email. Okay, I read every email. You sent a message and that happened. Kappa. What? Very strange. Why is Kappa, the Greek letter, bound to moon emoji? This is very strange. Huh. The README has a link of web page that you're adding characters for. Yeah. Anyway, so yeah. Anyway, it's just a cool project, which I think is, I'm considering contributing to it at some point. One of the cool things is, like, you can dump, I believe you can dump multiple characters in, not just, like, one character, so I'm interested in doing some extensions for it that get me all of my commonly used LaTeX tags. Because, like, to be completely honest with you, Mark, it's not that, like, it doesn't really save you any time at all if you just have to hit, like, the compose key instead of backslash to enter a lambda into a formula, right? And LaTeX doesn't really play nice with Unicode. So, so I would be interested in having a bunch of these that just, did my, like, if I could hit, like, compose GL and have it come up with a, or compose LL and have it LaTeX lambda, that would be, there you go. As long as all characters are completely escaped properly. Very, very important information. Pardon me. But yeah, anyway, any questions about the material or what? TextMaker disables the compose key. Oh, that's gotta be an option, though, that you can unset. Gonna go sleep now. 1:26 in the morning here. I'm... Of all of the people who I expected to be here synchronous with the lecture, it wasn't you, sir. Thank you. Thank you for being such a diligent student. Okay. Anyway, I'm probably gonna go lay down. Have a nice weekend, folks. Happy Halloween. All that jazz.